Okay, this is the video that's going to take you through the significant digits and measurement POGIL. And the way we're going to do this is you're going to start by working through the problems 1 through 7, and you'll notice when you get to 7, right after that there's a stop sign. So you're going to stop at that stop sign and then come back to this video. So pause it, attempt problems 1 through 7, then come back to the video and use the video to fill in any gaps, check and see if your answers are right or wrong, and make sure you've got your understanding down. Okay, at this point you should have completed problems 1 through 7. If not, go back and do that now. So we're looking at Model 1, which is a ruler that only has 2 markings on it from 0 and 10, and they say they're in centimeters. And number 1 says, what distances can you be certain of on the ruler in Model 1? Let me see if I can draw this. So there, this mark here is 0 centimeters, and this mark here is 10. And the thing we're measuring is like that long. What I notice is that the center of the ruler is right about here. So we're definitely below the center somewhere. Beyond that, you're going to have to do some guesswork. I may not have drawn this to scale very well, but the one I've drawn, let's go by the one I've drawn just for the sake of argument here. If I, in my head, I can guess that there's like 1, 2, 3, 4. That's not even very well delineated. But so the one I've drawn is probably about the 4 centimeter mark or so. So that's going to be my guess. I'm going to guess that this little thing that I drew is about 4 centimeters. Now the one that I'm looking at on the model is a little shorter than the one I drew. It's probably closer to 3, I would guess. So maybe for the purposes of this video, I'll go ahead and say that a decent guess is 3 centimeters. I can definitely be... Well, can I even be certain of that? All I can be certain of is it's somewhere between 5 and 0. That's the certainty I have on this one. So, let's keep going. Let's say that's what I'm certain about. 2. 6 students use the ruler in Model 1 to measure the length of the metal strip. Their measurements are shown at the right. Were all the students able to agree on a single value for any digit in the measurement? So did they all agree on the 1's place, the 10's place, etc.? If yes, which value and digit they agree on? So let's look. I'm gonna go ahead and record these values here to make it easier for us to talk about them. So there's a 3, a 2, a 2.5, a 3.00, a 3 1/4. Give myself some room here. And a 3.33. So let's notice first off the first 2 numbers. They only talk about the 1's place. So both of the first 2 answers are making a statement that they know the 1's place. But they're also making a statement about the 10's place. Here. Notice that every single one of these students agreed that we were not higher than 10. And if you look at that ruler, that we can be sure of. We can be definitely sure that we are between 0 and 10. We are not above 10. So all the students agree on the 10's place. So we could say yes. And we could say the 10's place is something everybody agrees on. But if we look at the 1's place, not everybody agrees on the 1's place. Alright, because I see some 2's and some 3's. Now, I'm going to take this 3 1/4 and say that's the same as 3.25. And then, if we look further, we can say that not everybody agrees on the 10th's place, and not everybody agrees on the 100th's place. And certainly not everybody even made guesses in those digits. So the only thing people agree on is that it seems to be the tens place here, that we are between 0 and 10. All right, the ruler shown in Model 1 is not very useful, right? Because it only has 2 markings on it. But a measurement can be estimated. Discuss in your group how each student might have divided up the ruler by eye in order to get the measurement that he or she recorded. So when I did this, I did a visual thing, and obviously the drawings weren't on there. I made these up in my head, because this is just on a computer, so I couldn't really write. But I could definitely say that it was, like, the halfway point is really easy to estimate, so I could definitely say it was less than halfway, and that's about as good as I could do. I guessed 3. If somebody else had, or I guessed 4, but I think if somebody else had guessed 3, the human eye is not a very good measurement tool. So I would say that 3 or 4 is probably about as good a guess as any. So I used, I estimated halfway, and said I didn't make it halfway. All right. That's 3. Let's go on to 4. Now we get a real, or a more useful ruler. So they give us this, 0, 10, 5 is somewhere in the middle, 1, 2, 3, 4, 1, 2, 3, 4. That's not so terrible. Okay. And the ruler goes 1, 2, 3. So goes to right up to here. Looks like. Students obtained a better ruler in Model 2. What distances can you be certain of on this ruler? Well, this ruler, I can definitely say it's between 3 and 4. It sticks out just a little bit past 3. So, what distance can I be sure of on this ruler? It's past 3, but it's not halfway past 3. This would be the halfway point between 3 and 4. So it's somewhere between 3 and 3.5. This is what I can be sure of. So my best guess is between 3 and 3.5. That's my certainty in this measurement. Okay, 5. What were the students able to agree on? Were the students able to agree on a single value for any digit in this one? Now let's look at their student value. So we have 3.2, 3.1, 3.3, and we have 3, 3.25, 3.20. Notice everybody now agrees on the ones place. Before we agreed on the tens place. Now we all agree on the ones place. Not everybody agrees on the tenths place, though. And certainly not on the hundreds place. So the only certain digit here that everybody says is we know for certain is the 3. Based on this ruler. All right, 6. Go to 6. What feature of the ruler made it possible for the students to agree on a value in that digit? So let's compare these two rulers. This ruler had 1, 2, 3, 4, 5, etc. It had a marking every 1 centimeter. Every single centimeter had a marking. This ruler up here, every 10 centimeters had a marking. Remember, these are the ones I drew in. So only the 0 and the 10, and presumably if this was a bigger ruler, you might get all the way up here and have a 20. But these are 10 centimeters apart, as opposed to these, which are 1 centimeter apart. So what feature made it possible for the students to agree on a value in that digit? This ruler in Model 2, ruler B, had 10 times as many markings on it. It was divided up 10 more times than the ruler in Model 1. So I could say ruler B has 10 times more. We're going to call them graduations. A marking on a device used to make a measurement is often referred to as a graduation. You might remember this from chemistry last year, a graduated cylinder, or chemistry this year if you happen to be in a chemistry class taking this POGIL. So ruler B has 10 times more graduations then ruler A. Okay, and 7, key idea, because I've got a key there. There will always be uncertainty in any measurement. This causes variation in measurements, even if the people are using the same instrument. Compare the variation in the measurements made by the 6 students in Model 1 and 2, which ruler resulted in greater variation. Explain why that ruler caused more variation. So going up here to Model 1 ruler, okay, if we look at it, it had a line every 10 centimeters, and if we look, the variation is like 3. What's the high? Actually, the high is like 3.3, and the low is like 2, just 2. So we have a variation between 3.33 and 2. All right, so a variation of 1.33. That's the size of difference between the measurements that people made using this ruler. When we get down to these values, in ruler 2, the high is still 3.3. Someone still thinks 3.3, but the low is now 3. So that variation is now only a 0.3 variation. There's only 0.3 difference between the measurements on ruler 2, whereas there's a 1.3 difference here. So using this second ruler cuts down the variation. And he said there's always going to be variation, which you can imagine. Like, let's say I chop this ruler up. I'm going to go between 3 and 4 here and go. That was 5, so... Oh gosh, this is too small. 1, 2, 3, 4. 1, 2, 3, 4. Now, there's still room to guess there. The way I've chopped it up looks like it might be just above 3.2, 3.21 maybe, you know, assuming my lines there are accurate. But even then, you're going to have to do a little bit of guesswork. And you could chop this ruler up an infinite number of times and still have space between the lines. I guess if you did it an infinite number of times, technically the space between them would go to 0 as you approached infinity. That's a limit. But we would say that for any finite number of graduations, there is going to be variation. Some kind of variation. But that variation will get smaller as those lines get closer together. So, let's see if we can make a coherent answer to this question. Compare the variation. Which ruler resulted in greater variation? Ruler A had greater variation. Why? Ruler A, because its graduations, ruler A's graduations, were farther apart. So we would expect that the more lines you put in there, the closer together you put the lines, assuming they're all evenly spaced, and this is a decent measuring tool, the more accurate you can be. Or the less variation. By accuracy, I guess, to say, I'm using accuracy wrong. The more precise you can be with your measurements. The variation in your measurements is going to be smaller. The measured values by each person in your lab group are going to be closer to each other. And that's a good thing. Okay, we want high precision. Okay. So that was 1 through 7. Now we're going to go on to the next section, which looks like it goes 8 all the way up to 10. So only 3 more. So you're going to go 8, 9, and 10. Attempt those, pause the video, and then come back and unpause the video to see how you did on 8, 9, and 10. Okay, so you should have done 8, 9, and 10, and now you're checking your answers. If not, go back and do that first. All right, we're now looking at a ruler that has a lot more graduations than before. So it says, the students obtained an even better ruler, Model 3. A, were the students able to agree on a single value for any of the digits in their measurements? If yes, what values? So let's look. I'm not going to try and recreate the ruler because that's a lot of graduations. But notice they put 3.21, 3.20, 3.22, 3.2, 3.215, 3.205. Okay, look what they all agree on. They agree on the ones place, they agree on the tenths place, but they do not agree on the hundredths place. So we are now closing in. And you should see this as a pattern here. With ruler 1, we didn't even agree on the ones place. Then we added 10 times more graduations in ruler 2, and we did agree on the ones place, but we didn't agree on the tenths place. So we added 10 times more graduations, and now we all agree on the tenths place, but not the hundredths place. Every time you split this up 10 more times, you get one extra, looks like a decimal place that everybody agrees is true. And if I look at that ruler, yeah, I can definitely see that the edge of it looks like it's right about at the 3.2 mark. So A, we can say yes, and the place that they agree on is the tenths place, or the 0.1 place. And of course the 1 as well. They also agree on the 1 place. B, what do we got for B? What feature of the ruler made it possible for the students to agree on the values in those digits? So this particular ruler, it's got 0 and 10, and it's got 1, 2, 3, 4, but it's also got 0.1, 0.1. So this ruler, I'll try to write it as a full sentence. Ruler C has graduations at the 0.1 centimeter level. Okay, so ruler A, his graduations were every 10 centimeters. Ruler B, his graduations were every 1 centimeter. And ruler C, his graduations were every 0.1 centimeter. And so since every 0.1 centimeter is a line on the ruler, everyone can see, right? Everyone can see that that measured object goes past or up to at least the 0.2 line. So there's no way to be uncertain about that. Everybody knows that has to be true because those are the lines on the ruler. All right. 9. Oh, wait, I have to read this. Read this. When humans use measuring instruments, variation is expected. That's because your eye is not very good. We think it is, but it's really not. Everyone will estimate differently between marks in the instrument. On the other hand, digits that are certain, based on the marks in the instrument, should not vary from person to person. So if we're all using the same ruler, we should all agree that it got to the 0.2, or the 3.2 rather, level. We have to at least agree on that. Okay. Now, on to Model 4, valid measurements. So, the measurements taken in Models 1 through 3 have been combined. The measurements that follow the rules of measurement agreed upon by scientists are in the valid measurements column, and those that do not follow the rules are in the invalid measurements column. For each valid measurement shown in Model 4, draw a square around the certain digits, if any, and circle the digits that were estimated, if any. So, I'll redo these. 3 and 2, and then this was 2.5, 3.0, 3 1/4, not 0.1/4, sorry, 3.33. I'm just going to do the first one here. We'll go back and do the others as well. So, draw a square around the certain digits and circle the digits that were estimated. Remember, in ruler A, we were not certain about the ones place. We were only certain about the tens place. So the square, if anything, would be this here, the tens place. We were certain that that was not a 1. It was a 0. It was between 0 and 10. Or below 10, so. But we were not certain about this. These are valid measurements. We were not certain about the ones place, so we were not certain here. Definitely. And we certainly weren't certain about any of these. Okay? So, that was for ruler A. For ruler B, let's put those up there. We had 3.2 is valid, 3.1, 3.3, and over here you had 3, 3.25, 3.20. Okay, now we were certain about the ones place. If you look at ruler B, everybody agreed on the 3. We were certain on that, and especially because there were lines every 1 centimeter on that ruler, so there was no way not to be certain unless you read it wrong. It would be a mistake not to be certain about the 3. But there was variation in the ones place. There was definitely variation here. We were uncertain. We couldn't be sure whether it was a 2, a 1, or a 3 with our eye, and that's because human eyes are not very good. And so these digits were all uncertain. And then if you go on to the last one, it was 3.21, 3.22, and 3.20, and the bad guys over here were 3.2, 3.215, 3.205. Okay, so with this ruler, there were lines every 0.1 centimeters, so we were happy with the ones place, we were happy with the 0.1 place. Those are all certain measurements, because we had lines. We have lines for those measurements. We don't have to rely on our eye to guess. We did here, though. There was no 0.01 lines, so we had to guess here. Anything after that. All right. For each value, so draw. It was just drawing. All right. Going on to number 10. Based on the examples, circle the best phrase to complete each sentence below. So let me make some sentences here. In a valid measurement, you record what? 0, 1, or 2 estimated digits. Estimated digits. Okay, so we have to figure out how many estimated digits. So keep in mind the left side were the valid digits. All right. So looking here, that's our estimated digit. That's our estimated digit. These guys were not valid. Keep in mind, so we can't count them. Okay. All right. Over here, we had one certain and one estimate here, and then here we had 2 certain and 1 estimated. So in all 3 models, the valid measurements, according to professional scientists, are the ones that only estimate 1 digit. Okay, so in a valid measurement, you record 1 estimated digit. Okay, that's 10A. Here's 10B. In a valid measurement, I'm not going to write that again. Okay, the estimated digit is the, and then I have choices, the first digit, the second to last digit, or the last digit. Well, let's look. It's all the ones I underlined on the left side, not on the right. And I underlined the last digit every time. Okay, so the one that I circled or underlined, it was the last digit. So the last digit in any measurement is estimated. Okay, that's the one with the bit of uncertainty to it, or variance to it. All right, C, in a valid measurement, the estimated digit corresponds to largest, smallest, 1/10 the smallest mark on the instrument. Okay, so we're comparing the estimated digit to the smallest mark on the instrument. Okay, so we go up here. Here the estimated digit was the ones place, and ruler A did not have values at the 1. It had 0 and 10. Those were the only 2 markings on ruler A. So it had values every 10, or the tens place were marked, and the estimated digit was the ones place. Okay, ruler B, here in the middle. These guys are estimations, and they are the 0.1, the tenths place. But if you look at ruler B, it was 0, 1, 2, 3, 4. It had definite markings at the ones, the ones column. So we estimated one step further than the ones column. And ruler C, these estimations are the hundredths place, meaning, but when you look at ruler C, it didn't have markings at the hundredths place, it had markings at the tenths place. So ruler C had one more place than what was marked on the ruler. Our value, our reported measurement was one more mark than what was on the ruler. So it's not the largest mark on the ruler. It's not even the smallest mark on the ruler. It's 1/10 of the smallest mark on the ruler. So the estimated digit corresponds to 1/10 the smallest mark on the ruler. So whenever you're measuring, this is huge, okay? If you have a ruler like this, like ruler B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'll put a 0 in there as well, and you have something like this, right? That's the third mark. And you tell me that is 3 centimeters long, we're assuming this is in centimeters, that is not a proper measurement. I agree that it almost lines up with the third line there, but that's definite. Anybody can be definite. You can be just a little bit more. If I put a little dotted line there, okay? I see that the end of that object is just past the 3. You can estimate that that's, I don't know, 0.1 or 0.2. 3.1 is a much better answer. It's 10 times better, actually, if you divide it by 10, right? The tenths place is 10 times more precise than the ones place. Okay? So always do that. Don't leave off digits. Okay? Even if you think, let's say you thought that the end of that object was right underneath the 3, even if you think that's the correct measurement, you would write it like this, 3.0. Because you don't want to stop at what's definite. You want to go one digit further than what's definite. And what's definite on this ruler is 1, 2, 3, the ones place. So always go a step further in measuring. Okay, we're on to the next section, which looks like 11 through 16. So you are going to attempt 11 through 16, pause the video, attempt 11 through 16, and then come back and unpause the video and see how you did. All right, 11. Using ruler B from model 4, Tony recorded a measurement of 3 centimeters. Explain why this was an invalid measurement. 3 centimeters. Well, like I just said, if you have a ruler, and I just did this one up here, if you have a ruler like ruler B that has every single centimeter is marked, you can estimate further than that. So Tony should have gone and said one digit further, 3 point something, either 3.0 or 3.1. Any of those would have been fine, but he had to give me an extra decimal to be correct, because his ruler was that accurate. Otherwise, you're losing accuracy. Don't waste the accuracy that somebody took the time to write into the ruler. 12. Using ruler B from model 4, Dion recorded a measurement of 3.20 centimeters, which was invalid. But when Maya made the same measurement using ruler C, it was considered valid. Explain why the 0 is acceptable when using ruler C, but not when using ruler B. So they both record this, 3.20 centimeters. But this is okay with ruler C, but you can't do it with ruler B. Why not? Well, look at ruler C. Ruler C, the lines are 0.1 centimeter lines. 0.1, 0.2, 0.3, etc. But the lines in ruler B are every 1 centimeter. So this is C, this is B. 1 centimeter. If you're at 1 centimeter, you can guess to 0.1 centimeters. But if you're at 1.1 centimeters, you can guess to 0.01 centimeters. So if they both guess to 0.01 centimeters, that assumes that they're using a ruler that can measure to, that can measure to 0.1 centimeters, if they're guessing to the hundredths place. But only one of those rulers measures to the hundredths place, which is C. B doesn't measure to the hundredths place, it only measures to the excuse me, B doesn't measure to the tenths place. It measures to the ones place. So we can't guess two decimal places away. That's not allowed. A student recorded the length of a test tube at 5.0 centimeters. Which ruler in Model 4 was the student using? Explain. They did 5.0. And the last digit, I'm going to put a little line over it, the last digit we know is the one that they guessed at, which means they had to be certain to there, but not further than there. So the ruler they had only measured to the ones place. And the one that measured to the ones place, this was ruler B. Okay? 14. In Model 4, Ricky recorded his measurement, 3.19 centimeters, using ruler C. His classmates thought he was wrong because his second digit was not a 2. However, Ricky's recorded measurement is perfectly valid. Explain. All right. Let's go back up to the drawing here and make sure. So Ricky is making an ooh, I have issues with this answer. I really do. Or with this question. So I'm going to blow it up here. Let's say that we had, that was a 3, that was a 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, they got a little scrunched at the end. This is the only time, so let me draw the object here. This is the only situation where I would support this kind of measurement. So let's say I drew an object like this that looks like it lines up perfectly. Well, if I'd drawn it better, it would look like it lined up perfectly with 3.2. Now again with this ruler, since that's the 0.2, that is certain, right? More or less. So we can guess one further than that. We could say 3.20. But if you had better eyes than me or thought you had better eyes than me, you could claim 3.19. If you thought it was just this side, just on this side of the 0.2. And I would say that's okay. You know, 3.19 because it's like edging up to the 3.2. Totally all right. You could also say 3.21 if you thought it was just slightly on the other side, the right side. That's like the only time I really endorse that kind of variation or that kind of guessing. Because imagine this situation, and I have to erase a little bit here. Erase? No? That's not going to let me. Okay, so imagine this situation. That I have the same object, but it goes out to like here, and we'll say that it comes in right about there. That's definitely between 0.2 and 0.3. So it's bigger than 3.2 and smaller than 3.3. If you ever measure an object like this, and it's clearly between two graduations, you can't say that that's 3.19. I'm going to say that's illegal. Okay? Now, if you scroll up, and I think this is the saving grace, if you scroll up to the ruler C in Model 4, and you look as close as you possibly can, there's an argument to be made that object on ruler C comes between the 3.1 and the 3.2. So in that sense, I would tend to support that and say that everybody who said it was above 3.2, they're probably off. Okay? In general, though, unless it's right on the line, unless it's this case right here, that alone allows you to guess either slightly above or slightly below, maybe. But even then, I have a real trouble guessing above and below a graduation. So technically, an instrument like this, yes, you can make guesses like that are in the right digit, in this case the hundredths digit, because we had a 0.1 centimeter ruler, and those are valid guesses. But let's make a further statement in this class. They got to be between the two lines that they're between. Okay? All right. Tricky. Moving on to 15. All right, when a measurement, oh, I got to read this. When a measurement is recorded properly, all the digits that are read directly, certain, and one estimated, uncertain digit, are called significant digits. The number of allowable significant digits is determined by the marks or gradations. They say gradation, I say graduation, on the instrument. Sometimes a 0 is the estimated digit and must be recorded. So for 15, record the length of this wooden splint. Notice that this wooden splint has markings every 1 centimeter. So, or sorry, the ruler has markings every 1 centimeter, and it looks like it's almost at the 7th centimeter. 7 centimeters would actually be an incorrect measurement, or an invalid measurement here, because the graduations are every 1 centimeter. 7 is definite. You have to estimate one digit further. So to do this correctly, this would be 7.0, where that's the estimated digit. But you're estimating that it's 0. That it's not above or below the 7 mark. And that's perfectly legitimate. Okay? So 7.0 would be correct for 15. And then 16. Ooh, that's an interesting one. Okay, 16 is actually the same length splint. If you look from 15 to 16, they use the same ruler and the same length wooden splint that they're measuring. They just added more graduations on the ruler in 16. In this case, though, the ruler in 16 is accurate to the 0.1 centimeters. So if you wrote this, 7.0, you're also wrong, because the 0 in this case, excuse me, I didn't mean to circle it, the 0 in this case is definite. You have to go one more. But if you still say it's not above or below, you would say 7.00 centimeters. That's how accurate that ruler is. And so think about this. If some student looks, oh, that's right on the 7, they go, it's 7 centimeters, they are wasting 10 and 10 again, or so they're wasting 100 times their accuracy or their precision. They are 100 times less precise. This number is 100 times less precise than that number. So don't waste your precision. Okay? Don't waste it. All right. On you go. You're going to do the last 3 questions, 17, 18, and 19 in the extension section. And then you're going to come back to the video and check your answers on the video. Almost done. Okay, you should have finished the POGIL by now. If not, go back and finish the POGIL. We're looking at 17, 18, and 19. So 17 says, when using an electronic device, such as a balance, measurement displayed on the screen is assumed to have one estimated digit included. In fact, you'll often see the estimated digit changing rapidly because there is fluctuation in the estimate. Explain why it is important to record the 0 in the measurement shown to the right. So you may have noticed this when you use balances, electronic balances, that like 1.20 is what it says, but if you let it sit for a while, you might see it go to like 1.21, 1.22, so this should be 1 right there, or like 1.19. Sometimes it bounces back and forth. Okay, that's okay. That happens, all right? That's part of the uncertainty of the machine. The machine is having a tough time keeping that balance at the right height, because that's how whoever constructed the machine couldn't make it more precise than that. So that last digit right there is the uncertain digit, and you would write 1.20 for that particular machine, meaning that these are definite. The machine knows those are definite, but the machine is having a hard time controlling or zeroing in, as it were, on that last digit. So that last digit is considered the estimate. And if you don't write this in, you're wasting 10 times your precision. Don't waste your precision. All right, 18. Consider a 1,000 ml grad cylinder with marks every 100 milliliters. A student records the volume of liquid in the cylinder as 750 milliliters. Is this a correct measurement? Explain. Let's see here. Every 100 milliliters, right? Every 100 milliliters is an acceptable certain measurement. So when we guess, we have to guess at the tens place. We can guess to 10 milliliters. And what they wrote is 750 milliliters. So looks like they did guess at the 5, because there wasn't like a 50 milliliter line. We know the lines are only every 100 milliliters, so there aren't lines every 50. So they guessed at that 50. Sure. The tens place is a guess. So I will say for A, this is part A, we'll say yeah. They correctly guessed 1 digit further than their instrument allowed. Part B, are all of the digits in the described measurement significant? Ooh, thinking about this. So the significant digits include all the certain digits plus the uncertain digits. So this digit is certain, this digit is uncertain. But we can't go farther than that. The last significant digit in a number is the one that you guess on. So this 0 here doesn't count. It's not the guessed digit, okay? So we'll say that there are 2 significant digits in this particular measurement. Because we can't keep guessing at digits. We couldn't say something like 751.32, right? If we're guessing here, that's as good as our eye can do. Our eye can guess about a tenth further than the marks on the particular instrument. We just can't see farther than that. You got to get used to that idea. So they left this 0 blank, essentially. All right? Let's keep going. A student properly records the length of a block as 120 centimeters. Draw the markings on the ruler that was used to measure the block. Okay. All we know is that's 0 centimeters there. They properly measured 120 centimeters, which means... Ooh, that's tricky. There are 2 correct answers for this. One of the correct answers, just like we did up here, was we guessed at the 5 or the tens place, and we did not, and so that meant that this marking was every 100. The 100s places were accurate. So if we want to do that on this ruler, we can do the same thing, right? We could say that the 2 is the guess, meaning that this is what's marked, and the tens place was not marked. So if we measure every 100, that could go like this. 1, 2, that could be 0, 100, 200, meaning that the block probably looked like that. And we're guessing it's 120. But there could also be this case. What if this was accurate and the 0 was a guess? That's possible. That would mean that there was a smaller mark here and a smaller mark here, etc. Like they kept going. I didn't chop that up enough. But like if that was 110 and 120 and that lined up perfectly with the edge, then you would say the 2 was accurate and our guess is the 0. But we're guessing 0 because we think it's lined straight up. That is also okay. So you could have marked your ruler every 100, or you could have marked your ruler every 10 centimeters, and either way would have been acceptable. Now I'm going to make a statement here about zeros. If you write 120 versus 120, depending on the object you measured, if you measured every 100, right, if this was certain and that was your guess, you would write it just like that, 120. If this was certain, and this is your guess because you had markings every 10 centimeters, people generally write that like this, 120, decimal place. But they don't put zeros after the decimal. So if the ones place is the guess, the decimal usually goes after that 0, just to make sure everybody knows that you guessed that 0. You measured the 2 and you guessed the 0. If you measured the 1 and guessed the 2, don't put the decimal in. a simpler way to do it is to put the line above them like I'm doing. If I write this 120 line, I mean that has 3 sig figs in that number. So the line is the ultimate giveaway. In fact, sometimes when you're doing math, you will get numbers like, if I had to plug this in my calculator and multiply it by something, right? Because we're eventually going to do algebra or calculus, depending which class you're taking, with these numbers, and you take that 120, you multiply it by something, you get some answer. I'm going to make up a number here, 251.3217. Right, you're going to get some repeating decimal, and it keeps going. I'll just say that it keeps going. But you need to let everybody know there are only 2 sig figs in that number. You are perfectly justified in putting the line over there saying, that's the number I guessed at. Even though there are a lot more digits in that number. And that happens all the time. Okay, so that's your significant digits in measurement POGIL. Keep in mind, you can always go 1 digit further than what you can see on the measurement device, than where the lines are spaced on the device, and you should always record your measurements 1 digit further than the lines on the device.